So, we will work out some examples to just get feel for Fourier space representation, and the examples are very, in fact, they are identical examples what we did in real space. Okay. And there will be some more work in later part where we try to derive some ODEs. So, that part will be later. Okay. So, example 1. So, this is what I showed you. So, this is a velocity field for in a box of size pi pi. So, this is pi is a 2D field, no, pi 0, and I had mentioned this. So, it was going around not quite circle, but is some kind of this roll. In fact, that is convection roll. Now, how do I put the arrows? So, to get so this x axis and y axis. So, at x equal to 0, which is this line, my y component, I should look at y component here. So, at y equal to pi by 2, y equal to pi by 2, this is 1 and x is 0. So, that becomes negative. So, it should be going like that. So, this field is going like this counterclockwise, and you can draw for various contours or streamlines. These are basically streamlines. Now, this was in real space, we did this before. You can compute vorticity, you can compute helicity, and so on and so on. Helicity 0 is a 2D field, but you can compute entropy and so on. Now, in Fourier, so which are the non-zero Fourier modes for this? How do I do the Fourier transform of this field? Concrete, all those formulas were nice. So, it has lot of Fourier modes, in fact 4 Fourier modes. Oh, precisely. So, let us write the first part u of x, which is 4a sin x cos y. So, I am going to put this 4 as 2 times 2. So, in fact, 2 had this 4 had certain meaning why I had put 4. Now, 2 sin x, it is a, sin x is e to the power I x minus e to the power minus I x by I, by 2 I, but 2 got cancelled. So, I, and cos y is e to the power I y plus e to the power minus I y, that is it, 2 cos y. Now, we can write this is a 2D field. So, I write this a by I e to the power I x plus y I. So, there are 4 terms for I. So, this with this one will be minus y minus e to the power I minus x plus y minus e to the power I minus x minus y, correct. Now, what was the definition of Fourier transform? So, u of x in 2D, okay, 3D also you can write, it is u of k x to the power I k dot r. Now, k dot r is kx x plus ky y. Now, I just compare this form with here whatever I got. So, you can easily see what is kx and ky. So, the 4 sums, this sum is for all k's. I know the 4 sums means there are 4 k's are involved, correct. This is just easy way to see. So, this one is kx is 1 and 1. So, I will write this as kx ky. The first one is kx, second one is ky. This one will be 1 minus 1, right. Kx is 1 and ky is minus 1. Third one is minus 1 1 and fourth one is minus 1 minus 1. So, this field u of x in real space is composed of 4 Fourier modes. And what are the amplitudes of these Fourier modes? So, first, this u of k is the amplitude. So, the first guy has a by I, a by I is in front, second one has a by I. third one has minus a by I, fourth one has minus a by I. So, this is how you pick out the Fourier modes. When I say Fourier mode means it is the amplitude of the Fourier mode. All this is an entity, this is an object Fourier mode which has amplitude and also associated wave number. Okay. So, this is what I have in the table. Okay, so, this is what I wrote. So, I think well, let the red be in the background, you focus on this black box. So, this is kx ky. So, maybe I should erase the red, should I? So, you have to remember which was a by I, and now I will ask you, well, you already have written in notes. So, which one is a by I? The first one is a by I, and this from here 1 minus 1, 1 minus 1, this is a by I, and this is minus a by I, and this minus a by I. Okay. So, I have in the table. So, there is a table which, so this is, I say x by x y means it is kx ky. Okay. So, this is in Fourier space. So, these are four wave vectors. We can draw this vector, and every wave vector has certain x component, y component, u. So, this is what I got. So, let us erase this as well. Yes, yes, but I interchangeably use x and y. So, this Fourier space. Now, so the same way I can also compute u of y. So, these are, so this is what I computed. So, this is what, this is u of x and these are u of y. Now, some interesting pattern. So, do this satisfy the incompressible condition? They should, right, because we showed in the last, well, not last lecture, but one of the lectures where this one satisfies incompressibility, del dot u is 0. So, that means k dot uk must be 0, and is it the case? So, it is this kx and this ky. So, kx times this one plus ky times this one must be 0. So, is 1 1, so simply add. You can do this one 1 times this and minus 1 times this. So, all Fourier modes satisfy that k dot uk is 0, and it better be because it is incompressible. Okay. Now, what is it? I will not work out, you can just work out k cross uk times I. Last one is minus 1 minus 1. So, yeah, this should be plus. So, k dot uk is 0. You can compute u of omega of k is like this, okay, and you will find that it is only z component. So, this will give you this one. What about kinetic energy? We call it modal kinetic energy, energy of a mode. So, instead of saying kinetic energy, which is for the whole box, modal kinetic energy is the mode of energy of a mode. So, how do I get this? Half of ux squared plus, actually it should be mod, ux is also a complex number, mod ui squared. So, take mod of this, which is a squared, mod of this is again a squared. So, there are 2 a squared, divide by 2, it is a squared. So, this is the energy of the first Fourier mode. So, all of them have same energy, all Fourier modes a squared. Omega will be just same. So, basically what is the this is modal entropy, which is half mod omega k squared. Okay. Now, omega has, it is a vector, but it is only one component. So, you can just take the mod of this, which is 4a squared divided by 2, which is 2a squared. Okay. So, this is how we compute for each mode. Now, this looks trivial, but you should be able to do this for any configuration, and I right now have only a single mode, but we will have more. Well, not single mode, 4 modes only, but I have pretty one function only, but I could have more functions, which I am going to come to it in a while. Okay. Now, what about the direction of the velocity field? So, you can also see this is nice. So, this velocity field has ux component and ui component. Now, these are not in real space, but it is fine, I can also have a Fourier space. So, a by I and minus a by I for 1 1 1, this is my 1 1 Fourier mode. So, a by I, which will be like this, and ui is the same length, same complex length, but the same length with a negative sign. So, it is like this. So, my u vector is like that. Okay. So, this is my u of 1 1. It better be perpendicular, and it is indeed perpendicular. Okay. Similarly, you can draw for other wave numbers. Now, one more thing you will notice, that is 1 1. So, reality condition, do they satisfy reality condition? What is reality condition? U of minus k, u of minus k is u star of k. So, let us, this is minus k, right. So, this, if this is k, this should be minus k. For this, it must be complex conjugate of u of k. So, it means complex conjugate for both the components. So, this is indeed complex conjugate of this, and this is also complex conjugate of, and same thing can be. So, whatever number, complex number I get here, ux and uy, this must be complex conjugate. So, if this is alpha, then it must be alpha star. If this is beta, then it must be beta star. Okay. So, this table must satisfy these properties. Okay. So, everybody is happy with this example. Okay. And so, incompressible condition is k dot uk is 0. Vorticity you have to say I k cross u k. So, you do not need to do curl, but you have to do this cross product. Now, example 2. So, this is again familiar one, cyclone, anticyclones, lot of them. So, what are the Fourier modes? So, first identify the Fourier wave number. So, this one, so sin y is, well, I put a factor 2 again in front. So, minus 2 sin y, it is e to the power I y minus I y by minus I. So, like that. So, I will go up, right, minus. So, I just multiply by I. So, this I will go. So, I got, so I y means what is wave number corresponding to this one? So, k y is non-zero, k y is 1 and k x is 0. So, this one. So, this is corresponding to this one. What about this one? Below 1. Okay. So, we have 0, minus 1 and 0, 1. Sin x corresponds to 1, 0 and 0, 1. Okay. So, these are, this corresponds to this guy. So, what are the amplitudes? So, let us write down the amplitudes. I am going to draw this, in fact, let us get rid of this. So, here at 1 0, this one. So, it is sin x is 1 by I, 1 by 2 I. So, 2 gets cancelled. So, 1 by I. It has y component. So, this is minus I. So, here I got minus I and y component. So, let us draw like that. Here it should be just opposite in the left. So, this will be like that. So, S k dot u k 0 is satisfied here. 0 1, this is plus I. So, it is like this and like this. So, in fact, these are like nice fan, this is what we got. So, we can make a table. So, table is ux is, so these are standard, I just do exactly same way, and I get omega z is, for all of them they give positive omega z. Okay. And so, I will not, I mean, I just did this and you can easily fill the table. So, 1 0 this one, 1 0 is this one, it is only y component 1 by I. So, this is minus I, this is what I had written, minus I, and 0 1, this 0 1 is here, this x component is non-zero, this x component. So, I got I sitting here. Okay, now we will do slightly more work and we will make this one non-zero. I will put a uz component. So, this is 2D field right now, but now we will make it 3D, but 3D where the field depends only on x and y. So, it is a very strange kind of field. So, this field is called quasi 2D field, or actually no, it is not quasi 2D, it is called 2D 3C, 2D but 3 components. So, if I go up in that z direction, then I get basically it is not function of z. So, it is same configuration, but it has 3 components. So, this is the third component. So, it is not purely 2D field, it is a 2D but 3 component field. Okay. So, this part is exactly same as before. This in fact, if you have written is exactly same, but I added this new uz component. So, these are same as before, the two ones, but now we have uz. So, uz is for 1 0, 1 0 has what is the uz? Cos x, it will come from cos x. 1 0 means it is x component, so that will give you 1, and cos y corresponds to 0 1, 0 1 and 0 minus 1. So, these are all, but all of them have magnitude 1 or amplitude 1, because 2 is sitting in front. Is that fine with everybody? So, 2 cos x is e to the power I x plus e to the power minus I x. Okay. Now, I get in Fourier space 2, I get basically some of them have ux 0 and ui, this is uy and uz, and this guy has ux and uz. So, in Fourier space 2 we get this strange combinations, 3 components sitting there. You can compute vorticity by again doing k cross uk easily, and well, I will not do it on this paper, but you will get this. Now, you can see that, now I will delete all this stuff. What do you see for this example? This A example is here, no? A example is here, and B example I will mention it a bit later, but just focus on this one, first one, this example. Omega and k are exactly same. Now, this is strange, right? So, omega is curl of u, but how is omega can be same as u? Okay. But you see, so we can have the I sitting here, it is possible. I have no, I mean I am not cheating anything, this you can just work it out, you will get this. And we saw that in real space too, omega was same as u. Okay. In fact, what happens is this somewhat interesting. So, this z axis is perpendicular going in that direction. So, now we have ux and ui, this x axis, y axis. So, my velocity field has these components. So, this I said both here for a Fourier mode, both, well, the two components are non-zero. Actually, it's not x y, it is x z, y z, y z, y z, y z. For this one, y z is non-zero. If I take the curl, they just swap. So, y contributes to z and z contributes to y, and you reappear as before. So, that is what happens for these kind of fields. Okay. So, since u and omega are in the same direction, in fact they are identical, it is maximally helical, it is 1. Okay. I use the formula half u dot omega star, real part of this. Okay. So, you can just do this, this one dot u omega star will be plus I for the y component. So, minus I times I is 1, right, and 1 into 1 is 1. So, basically get 2 by 2 is 1. Okay. So, one important point to note is that it has two components, a real part is 1 and imaginary part is minus I. You see here, now we proved, no, I said real cross imaginary dot k must be is a helicity. So, the real is 1 which is along z component, imaginary is minus I, but is along y direction. So, y cross z is x. Now, k is along x direction. So, k dot u real cross u imaginary is finite and it happens to be 1. So, you can compute them by that formula, you can just compute and you will find this is what you get. So, real and imaginary here both are non-zero and they are perpendicular in fact, and that was maximally helical, it is y and z direction. So, it is same for this property holds for all of them and all of them have positive, in fact maximal helicity, maximally positive helicity. Okay. And this was the example where we had cyclones and their anticyclones, so like that. Okay. So, this picture is we did before. Now, what about B, example B? Only difference between these two is the sign here, these two minus signs, there is no difference. So, as a result my uz is here. Okay. Now, you can see the difference for this u and omega are opposite, u and omega all of them are opposite. So, u dot omega will be giving a negative sign and negative sign here. So, in some sense omega is going like this, cyclonic, and uz is in the same direction, no, this we saw uz, then it is positive. But omega going like this, but uz is negative, then I get negative helicity. So, that is the picture we get here. Okay, so these are simple examples. So, we stop. Thank you.